start. So this is week number 4, lecture 8. So we haven't missed any yet. So it's 04 lecture A, so they are in number 7 of the PPT, lecture 7. Just so you know that today, after the class, we're going to have 1 hour tutorial session here, okay? Then our problem set number 2 will get due 2 weeks from today, okay? 2 weeks from tomorrow, okay? After the PS2, we're going to have a 1 week interval. So I get you warm up with your math. So last time we talked about state variable model and using this complete response formula. So this is a state response due to input, and this is the output C x plus du, okay? So x is like this. So all this is for general linear time varying MIMO system, multi-input, multi-output system. So this is very interesting. And we also learn about state transformation when you have x is p inverse z. So xt is p inverse t and z. Okay. So that's the transformation. Then you can see that the state transition becomes, the state transition matrix becomes like this. This is yours. So let's just review what we learned. So in general, then we can write, after the state transformation, we can write the output in terms of this. So I want to draw your attention about the P is invertible, okay? So we're talking about equivalence. If you say two systems are equivalent, then we say there exists a state transformation to transform from one to other, okay? So state equivalence. Then the special case is a time invariant system, and this is easier. Remember, we have T comma sigma in the state transition matrix, but now we have T minus sigma. Okay, T minus sigma. So that's a typical time invariant case. Because you write a T minus sigma, then you can treat this as well as this convolutions. Okay, so let me go back. Just remind you that this is not yet a convolution, okay? Not T minus sigma, okay? Not T minus sigma, it's not convolution. Only in time invariant case, this is a convolution. This AT convoluted with UT, okay? And if we use Laplace transform, we end up with state transition. You can SI minus A inverse. Okay, then transfer function is a 0 initial condition. You have a in and out. So input to output in between, we have internal states that is X. Okay, internal state that is X. So I want to draw this one with you. Okay, so you have an input U in here, output Y in here, inside the big box. Okay, big box. Okay, inside the big box is something inside. But if we have a closer look, we are going to have what? You have a C times X, but X is from X dot integration, while X dot is from BU, and you have X times A in here, okay? But now you also should say you have another direct feed-through term, is D in here. So we should know this type of internal representation. So inside here, we say this is input-output description, in-out description, and people using a transfer function of G of S to describe it. But inside, you really can have a state space representation. So that state is very important. So this is called state vector in the MIMO case. So this state vector is a realization, of what? Of the I/O transfer function G of S. So I hope this is clear to everyone. For the LTI, so the LTI system, if it is LTV, do you have this thing? No. There's no transfer function like that, okay? If it is time-varying. Okay. So anything we use here, because we have G of S, is because we can do LTI. Because of the LTI, then we can have eigenstructure. Then we talk about eigenvalues, eigenvectors. We talked about eigenvectors could be the fully sized linearly independent ones. So all in this case, A is considered as simple. So if I give you a matrix, I ask you, is this matrix simple? What does that mean? Its eigenvector has n linearly independent vectors, okay? And because of that, it can be diagonalized, okay? Make a diagonal, okay? Diagonal. So otherwise, the A must be transformed into Jordan form. So in that sense, I hope you see this model decomposition part. So how you can find out diagonalization transform P matrix, so to make A and diagonal, okay? So we have to learn that. So then for the eigenstructure, you can write A matrix in terms of A, you put those P matrices, so be careful here. So this is identity, you didn't do anything. This is also identity, you didn't do anything. You put together is still the same as this, right? So, however, we can just pull out this as the case in here, then we become, this is a diagonal. So this is in a simple case when the A can be diagonalized. But there are cases when A cannot be diagonalized. When A can be diagonalized, so we can write in terms of, called W is left eigenvalue. W is a left eigenvalue. Left eigenvectors. So then you can write the solution in terms of, this is a time, this is called modes, okay? These are the modes, lambda 1, lambda n, and modes. So this is a left eigenvector, this is a right eigenvectors. So there's a P matrix and a P inverse matrix. So in the end, you write projection this one to initial condition, initial vector projecting on the W, and then your eigenmodes are projecting on this eigenvectors. So in the end, your X can be expressed in this way. So this is called, you don't have to memorize it, just so you know that this is a projection like in here, this is a projection like in here. So this is left eigenvector, this is an eigenvalue, this is eigenvector. So they are all connected like that. So in the middle, this thing is called the mode, okay? So projection of the initial condition on the left eigenvector, this is initial value. And so we have seen this already, and we are going to see eigenvector, modes, initial conditions effect, adding together you get to find a solution. So these are the different starting points. You will see all getting to the equivalent points. So we are talking about x dot is ax plus du, this x dot is ax plus bu, okay? And you usually design the controller such that in the end, so x dot is a plus b f x. So this is talking about a system that is stable for any x0. Then your xt will go to 0 as t goes to infinity. So that's a stability question. Okay? Stability. Okay? But before stability, I believe there are something more important than that. So before you even talk about system stability, you need to talk about what? Controllability. Because whether you are able to find out this F gang matrix, as if F is U is F times X, can you find this F to make this stabilized? So this is called controllability. And of course, we have a dual concept, it's called observability. So these, I will cover this one today, hopefully. Okay, we'll see if I have enough time. So I think those review of what we learned in the last week, we can be done here. This week, so we can summarize the model decomposition. We have seen that diagonalizability. Then we'll be able to do the model decomposition for inhomogeneous systems. We have convolution with this. So this is t minus sigma, u sigma, d sigma. So this is a convolution. And the c is of course c times v and wi times b. So it's bu. So I hope this is also simple. Right eigenvector, this is left eigenvector. So then if you do in Laplace transform, then this one will give you, these are all the modes, these are eigenvalues. So then this is all the modes. And remember, inverse, remember, S minus lambda I and e to the power of minus lambda I t is a Laplace transformation pair. Okay? Laplace transformation pair. But my question is, sometimes you have a squaring here. What are you going to do? What are you going to do? Okay? Maybe you forgot. Okay, but doesn't matter, okay? We'll remind you. In fact, it's also beneficial for all of you to know this type of, yeah, let me do this one for you. So it's a review, okay? So you can see that, one of S is a Laplace transformation pair of 1 ut, right? Okay, 1 ut. So this is a correct writing. Or you say is 1. But you need to put a comma in here, say greater than or equals to 0. Otherwise, you don't write this one, just say 1. That would be wrong, okay? Don't do that, please. Or you write something like 1 times ut. We know this is a unit heaviside function, so either way is okay. But I'm trying to say that, do you know what is the squaring here? Okay. How about this? right? Is this correct? No, you should write this one, please. If you don't write, I will treat it wrong, okay? So, okay. So what I'm trying to do here is, if you have f of s, then f of t. Okay, so this is a Laplace transformation pair, right? So what if I have s minus omega, okay? S minus omega. What are you going to get?
Right.
Is that right? It's a shift, right? So shift. So now, let's assume this is 1, okay? So this is S1, right? So from here, by applying this rule, what I'm going to get? So then it's like 1 e minus omega t, it will give me s minus omega, right? Okay? Make sense? So you don't have to memorize, you only have to memorize this formula and this, then you can derive all others. So this one is derived. This one to this one is derived from this formula. Okay, from this formula. So it's derived. Now, I'm trying to do the next one. Okay, next one. So I have t in here, I have this one in here. So I know that, what is t? So now I have ft is t, okay? I have t e omega t, okay? What is this one? Okay? T is s squared, so I have s minus omega squared. So this is t, okay? So I'm going to write here as a t. So I have square, I have t. If I have third, you have t squared divided by 2, right? You can keep going. So in other words, this formula is quite important. It's called frequency domain shift. It's equivalent to exponential weighting, okay? And same is true. You have e to the power of tau s f of s is equivalent to what? It's equivalent to f t minus tau. Okay? So frequency domain delay is equivalent to weighted e to the power of minus s times original fs. So of course this is the original pair. So then you can shift in frequency domain or time domain, and they have such kind of formula. Okay? So this formula usually were ignored by many people, but if you know this formula, then this can be derived. Okay, derived. So we're going to see that one immediately. So the reason we have multiplicity in here, that is exactly due to the Jordan blocks. Okay, the Jordan blocks. Okay. So in here we don't. We have all a distinctive. A is simple. A is simple, then we always have this thing. Okay. You can diagonalize it, so you have lambda I. So this is simple. You don't have square in here. So this also has a very interesting name. It's called PFE, partial fractional expansion. Partial fractional expansion. Now it's partial fractional expansion. So today we are going to cover two topics: discrete time solution and controllability and observability. On the other hand, let me go back to the previous slides regarding Jordan canonic form. Because I said we are going to have something like in the last week we mentioned about so we actually were talking about diagonal form. That means I can make the A matrix always, yeah, so these are the alumni, this is called distinctive eigenvalues. So then you always have n linearly independent eigenvectors. So those can be considered as a basis. And because of that, you can make this diagonalized A matrix. And also eigenvectors all form similarity transformation to make the A matrix diagonalized. Okay, so this is an example, so you can see it's all distinct. So the eigenvalues are 0, 1, 0, minus 1, and minus 2. Okay, so that's a simple case. Okay, that's a simple case. For each eigenvalues, we can solve eigenvectors. Okay. So, but in other cases, I have repeated eigenvalues, but we still have a full set of eigenvectors. So those are not distinct, can repeat, but still they still have n linearly independent basis. Same. This is the same as case 1. So then this is case, matrix is still simple. So when A matrix is simple or not, it's not like, oh, all the eigenvalues are distinctive. No, it could be repeatable. Or could you have a multiplicity, but its corresponding eigenvectors are n. There's a full rank that you have still have n linearly independent basis. So then we still call this matrix a simple matrix. Let's see an example. Then the last case is the most difficult case. It's called eigenvalues and less than n eigen. So it's not distinctive, and also you don't have n linearly independent eigenvectors. So there's a new basis for eigenvectors. Therefore, the matrix is not diagonalizable. So the example is like this. This is actually, to me, is a Jordan block. So you have eigenvalues. So they are repeating 1, okay? So, but you only have one eigenvector. You don't have another eigenvector, okay? Because that is a rank is 1. So you can transform the Jordan canonic form. So what is the Jordan canonic form? So basically you have you have p distinctive eigenvalues. For each eigenvalues, each p eigenvalues, qi is a linearly independent eigenvectors. So then all these adding together will have so many linearly independent eigenvectors. So for each linearly independent eigenvectors, you will have a corresponding eigen Jordan block. Okay? For each of the eigenvalues, you have multiple Jordan blocks. So then put together is a block diagonal matrix. So then finally, the overall matrix can be diagonalized in a block diagonal way. Each of these contains Jordan blocks like this. So let's see an example. I like this example. I like this example. So in this example, what is the algebraic multiplicity of this system? What's the algebraic? What is algebraic? What is the geometric? So I hope you can answer this question. So for geometric multiplicity is only 2 because you only have 2 unique eigenvalues. Okay? Okay, 2 unique eigenvalues. But how many eigenvalues do you have? So you have 3 blocks, okay? 3 blocks. So you have 1 linear eigenvectors for this one. So together you have 3 independent eigenvectors. So Q1, Q2, so adding together is 3. Okay? So you can see the, looks like we have eigenvalue is 1, and we have 2 Jordan blocks, okay? 2 Jordan blocks. Okay? So N11, N12 for first, the first unique distinctive eigenvalue, you have 2. There is one is 2 by 2, another one is 3 by 3. So the last one is 1 by 1. Okay. So this is like a J. So this whole thing is called J1. This is J2. Okay. Then this is J11 and J12. I think in the model analysis, I remember we have a slide. I remember we have a slide talking about there's a T. There's a T in front of. Now, if it is repeatable, if it is distinctive, that's easy. If it is not distinctive, then you should have a T, this one. Okay, this T. So that's because of the Jordan block. Okay. So today, let's switch to discrete time solution again. I think it's here. Okay. So this is in the discrete time case. So you should read chapter 20, 21. I gave you those. Chapter 9 also gave you a copy, right? So controllability, observability. Please read those chapters. Okay. And after the controllability, observability, we move to stability. Okay. I think it's more logical to talk in that way. But in our textbook, they talk about stability before they talk controllability, isn't it? Yeah. So chapter 9 is controllability, observability. So we are leaving the internal stability, chapter 6, 7, 8 later, okay? So let's get used to this. This is a linear time varying discrete time system. Okay, so LTV, linear time varying, okay? A is a K. If you do iterative process, giving K, you will get K plus 1. Giving K plus 1, you get K plus 2. This is called iterative process. By doing that, it continue, you get X, K0 plus 3, you get this. So you don't see the rule very well, okay? So we learned this in last time, and we can put all the multiplication into phi from K0 to K, then this is called state transition matrix. So if we condense the phi in here, so we can write solutions like this. So we have learned this before. And again, this is like this. So this is linear time varying case. Okay? Linear time varying case. And we also learned state transition, state transformation and what's the change. So you have pk here, again, this is time varying. For each of k, p is invertible transformation. Then, so we are having be careful what we use. K plus 1 and plus 1 plus 1, everything is plus 1, okay? Then we do both sides, okay? Pk plus 1, z plus 1 is x plus 1. Then you have this one. But you want to replace this, Okay, so what we do is xk we know is pzk as well, pkzk. Okay, so we invert pk plus 1 here. So you can see you have p in here, p in here. In continuous time, this is t, this is also t. But in discrete time, be careful. This is k, this is k plus 1. So the starting point is from here, this side, xk plus 1 side. So other than that, everything is easy. And, so if we have two discrete time systems equivalent, if there exists invertible pk transformation, non-singular, okay, it's invertible. So that's the time varying case. Let's focus on LTI, discrete time case. So A is a constant, B, C, and D are constant. And we have seen why A, B, C, D are constant is linear time invariant. We did that before, right? So then we can see we have a formula of a similar case. Multiplicating, you have to write A to the power of this k minus j. And again, so you can see this is also discrete convolution case. And why it can be written. You just put this one in here, you get this. So next I'm going to get you the Z transform, okay? Z transform is nothing but to introduce something. So Z transform, basically Z is like you have xk and xz minus 1. So this is called Z transformation pair. Z transform pair. Instead of talking about Laplace transformation pair. Z to the power minus 1, okay? So if I put a Z in here, xk, it will give me xk plus 1. If I do Z minus 1 xk, then it will give me xk minus 1. So this is like a shifting operator. I operate with this one, I will shift it back, okay, shift it back, or move forward. So Z is like that, okay, Z is like that. So then, if you feel this is sudden to you, we can derive this one ourselves. It's not a real hard problem. Let's do it. So this Laplace transformation pair, I hope you will memorize it. It's useful for you to understand a lot of things, okay? Like why you suddenly can say this square will, as if you are writing a T, okay? Okay. So I'm going to do this one for you. So you have a xk plus 1 is axk plus buk. But remember, I'm using k is xz minus 1. So I'm going to write, they are using a z. I hate it. It's okay, we'll just write this z. So what I'm going to write is z xz, okay, is a xz plus b uz, okay? So this is a z transform both sides, okay? Okay. So then I move this one this side, so I have zi minus a xz is b uz, okay? B uz. And then I'm going to have xz is z I minus a inverse okay, that's xz, okay? And so that's xz. But remember, xz corresponding to xk, okay? Corresponding to xk. So I can write xk corresponding to that. So then this is called zero initial state response. I don't have initial state, meaning my x0 is 0. What if my x0 is not 0? Okay, we need that. Okay. So because we are going to write xk is x0 plus, okay, those state transition matrix, okay, convoluted with my u. Okay. So that is the form. So let's focus on this one. This is the transfer. This is phi in here. Okay, phi in here. Okay. So that's why I have this x0 in here. Okay. And this term is this term. This z is my phi. Okay, my phi. X0 here is x0. Okay. But the question is, why I have a z in there? Why I have a z in there? Okay. Why I have a z in there? So what is this z? Okay. That is because I need one more term. I need one more term. Okay. So that z x this z is an extra because of this transformation of this a. Okay. So you can also do a z input-output transfer function like this. So yz is uz connected with gz. Gz is written like that. Looks quite familiar with our continuous time counterpart. So let me do one thing for you here, so to help you about a z transform. Okay. So I want you to understand what is the definition of z transformation. Z transformation is from k is 0 to infinity. Okay, you have fk z minus k. This one will give you fz. Okay, that's z transformation definition, right? And it's infinite. So if, say for example, my fk versus k looks like this. So this is 1 and 1, 1, 2, 0, 1, 2, 3. So it's basically kind of like a constant. Then this is 1. It's nothing but you have summation of z minus k. And we know this one is so this one is you have a z minus 1. So you have 1 minus z minus 1. You have 1 z minus 1 minus n plus 1. Plus 1. Then you send n to infinity, okay? Send n to infinity, right? So you send n to infinity. Right. So of course we assume this is going to 0 in the convergence region. That means I need z minus 1 less than 1, okay? Less than 1. So then this one go to 0. So in fact, the constant UK, okay, and z1 minus z, okay, is Laplace, is a z transformation pair, okay, z transformation pair. Okay. But if you say here, sorry, this is a to the power of k, okay, like something like this, is 1, so a to the power of k, okay? A to the power of k, right? Or you do something like this, is a less than 1. So a is giving a constant. So then, what you are going to do is, you have a minus here, right? A minus k. So it's like a minus, or in other words, it's like z divided by a. So you can write this one like 1 of a minus k, right? So 1 of a times z is like z divided by a minus k, right? So then everything is, so if you have a k, if you have a to the power of k, okay, and uk is a constant sequence, that will give you something like this. Z divided by a is like z divided by a, so it's like z a minus z, okay? Or z divided by a 1 minus z divided by a. Are you confusing? Okay. So now I want you to look at here. This a is capital A. A is capital A, okay? It's a matrix, but it doesn't matter, it's the same, okay? The same. So what are you going to do is, you have zi minus a minus 1. So this is zi minus a, so you do this, so you write something like this, okay? So this one you should, in the matrix form, you should write z times, z is a scalar, times inverse, or is this inverse? So this is a minus zi, okay? Okay? No, not okay. So this is z, this is 1. Then I have, this is z, this is 1. Okay. So I have zi minus a. So I'm trying to get you why I have a z in here, or why you have a z in here, okay? Z is a scalar, remember. You can put it anywhere. So why you have an actual a z in here, okay? So if it is a constant, if z is a constant, then you will end up with this. So this is correct. This is correct. This is correct. But if you have exponential, like a to the power of k, so you end up with this one. So you in the matrix form is something like this. This is exactly why we had an extra z in here. Extra z in here. This is very easily get confused. Okay? So I hope this derivation is clear to everyone. Okay? So now we are ready to talk about controllability and observability in half hour. I have these slides. So If it is not controllable and you control it, what are you doing? You are doing something that is not possible. Why you do it is waste of time, waste of energy, waste of resource. So we should study controllability first. So what is a controllability? How do we check this controllability? So giving A, B, C, D, those A, B, C, D, those matrices, and how do I know the system is controllable or not? We need to answer those questions. Otherwise, just control it, and it is not controllable. You are wasting your life. So, can the input affect all the states independently? Can I get to where I want? Okay. Get to where I want, meaning inside the state space. Okay. The span of X. Okay. Span of X. And they are, of course, linearly independent. They can span the space. So then this is called controllable. So if you already have an output, and can the state determine uniquely? Can I tell where I am by what I observed? Okay. So this is called observability. So this is not a problem for SISO system. So if you have a single input, single output, this is not a big deal, okay? But for MIMO, multi-input and multi-output, the answer is quite deep, actually. It's related to geometric and algebraic questions about the system. So let's return back to this system and talking about controllability. Let's give a precise controllability definition. So talking about controllability on a time interval, T0 to T final, for any initial state, okay, starting from anywhere inside the state space, there exists a control U such that the corresponding solution satisfy XTF is 0. Think about, you have initial state in here. Is there something you control authority you can find to steer? You think about to steer it, to steer it to 0. To zero means equilibrium point. So that's initial state space, final state space. So then you have initial, you have 0 in here. So any of this initial, you can find the U1 here. And from here, you also find another control, you steer it to here. So these are the one-to-one relationship. So then for X04, you don't find a control to steer this one here. So it's called not controllable. So in other words, inside the space, probably there's only subspace that you're starting from those subspace, then it's controllable. From this subspace, it is not. Okay? This exactly is the case for MIMO. Okay? You usually don't assume, don't expect they are all controllable. So this is probably only partially controllable. Okay? So it's called not controllable. So in this final state space, there's a region. It's not, you cannot find a control to steer it. You cannot steer it to, so that is, we use C as a controllable, we use O as observable. So reachable if you can achieve, okay? Meaning you can make the final state to any point, okay? Any point. It's called reachable to any point. So controllability and reachability is the same. It's the same concept. The reachable or controllable is the same idea for continuous time system. But for discrete time system, there is a difference. Okay? Or I will emphasize that later. So not the same for discrete time system. Controllable but not reachable. Okay? So this is you already reached to that for any of the k. Okay. But you can only achieve to 0, not any arbitrary x1. Okay. Controllable on t0 to tf imply controllable on any interval contains this one. That's very interesting. So if you have an interval containing t0 to tf, so it can be bigger. If you are controllable on this, does not imply this controllable on any interval that does not contain. So of course, that's true. Okay. So we study the controllability, we do not involve output equation. So we simply, in this case, controllable sometimes is called A, B controllable. So this A and B are controllable pair. Controllable pair. This is actually very interesting to think about it. So you have A is like a system. B is like control, how the control signal will get into the system. Okay? So depending on how you arrange your actuators, so this B structure is very important. Okay? So that's why it's A also very important as well. So A and B are combined to define the controllability. Okay? So sometimes the control signals, you may not be arbitrarily given. You probably only give a polynomial a given order, like B splines, and you only select controls in that format. So, but whatever, the controllability concept under some constraints, limitations, restrictions, still a controllability question. Okay? Observability, so we need to involve the y in here. So meaning u is observable on this time interval if giving any y, giving any u on this interval, you can find what? Not find x. You find when you started, okay, at what initial state? X is 0. You can find out what is your x is 0. So the idea is like this. So you have an initial state space, you have a measured time space, so you have a different initial state. So you have a control, you apply x0, you go to here, y3, here you get a y2, then you also get y2. So then, is this possible given y, given u, you find out that? So it may not, because you end up with same y, same u, you come out with two different initial conditions, so it's not considered as observable. Okay? So again, observable is your current output and apply the control. What is the initial state? X. Okay? And sometimes you say detectable if not only you want to know x0, but also you want to know all the xt. That's called detectable. So observability, detectability are the same for the continuous time system, but for discrete time system, it may not be the same. And again, if you are observable on certain interval, then any interval you contain this started interval is also observable. So it's very kind of similar, okay? Very kind of similar to the example we have seen. Okay, so all these definitions involve state and output. We didn't talk about input signal here. So because I want to know what is my x0, okay? So I can always minus, we started y tiered, is y minus all these sides. So then I end up with c, phi, and x0, okay? So in other words, I started a tiered system. X tiered t is the same as this, and y tiered is cx. So we have no u here. So in this case, we call it is AC observable. AC observable. Again, we are talking about time varying system. Some of you may have learned linear systems, but you only talk about when A and C are constants. We are now discussing about when A and C are not constants. So it's quite different. It's involved in gramians. Okay? So it doesn't matter if you have a continuous observation. So say for example, you have integrals of those linearly independent kernels. So in these cases, we still, observability still, concept still applies. So let's see how I can check the system is controllable or observable for a general time varying case. And I'm assuring you that you haven't seen this one before. Okay. Even you took linear systems. Okay. So now we are talking about controllability around T0, TF. So there exists a control to make my final state to 0 origin. So we are talking about variation of constants, okay? Constants. That means my x is a constant. My x is a constant, okay? And now let x dot is xt is 0, meaning this is my final state. Remember, we assume that, okay? We assume xtf. So then I go to initial state, this is state transition, T0 to TF, state transition, and this is not convolution, okay? So the first term, we can get all of Rn here. This is the first term. Because this is invertible state transition. So then that means we can get to any of this point in Rn. The second term, I need rows of this phi b. The rows of this independent, then the control can reach to any points. So in this case, we define a field is a mapping between U to the all Rn. If I can reach all Rn, that means my U can control the system, steer the system to anywhere you want, including the origin. So then this function, the mapping, is actually this one. This is integral equation, this is U, this is over F. So then if it is controllable, that means the range of this space is Rn. We don't have any question about here because this is Rn already. Okay, the only thing we need to make sure of that. So do you see this? Controllability? Controllability means you can use the U, exist the U. You can find the existence of U, that you can steer the state to the origin from any point, okay, to an origin. Then that means you need to make this mapping, the linear operator, full rank. Rn is a range of, this R stands for range, okay? Rn. So that's actually our controllability checking condition starting from here. But this is very hard to use. So we need to use some of the theorems that say this is easier to compute. So what they do is to integration of the phi b, b transpose, phi transpose. So this is a positive definite matrix, and if it is non-singular, okay? So the W is called gramian, okay? It's called gramian, okay? And I think it's single M, it's not double M, okay? Can you guys check? I think I made a mistake before. I proudly announce there's extra M in here. Okay. Gramian, there's no double M, just one M. Please. Okay. So that slide as well. So I want this is called gramian matrix, and I want this gramian to be non-singular, then my system is, so how to prove? It's sufficient and necessary, okay? So the gramian is invertible, again, it's wrong spelling, only one M. So assume there is a inverse, exists inverse of the W matrix. X0 is giving but arbitrary initial state. So the U can be constructed as this one. This is a constructive. So B, so U is, so you have a U, you do this. So this is as if you didn't do anything, right? So this, no. So the inverse like this. So this is constructive of my U. They can drive the initial state to the origin of TF. So that is the applied control signal. So why this can be done? Let's try. So TF will be TF to 0x0. So you have phi BU like this. So we know this solution a long time ago. But remember, I'm going to insert U is a B, T, phi, transverse, W, inverse, okay? And then X0, okay? So I'm going to show you. So you can imagine that this minus sign is here, phi copy, B sigma copy, and there's a B transverse, phi transverse, W inverse, and D sigma. Remember, this D sigma, X0, this one, nothing to do with sigma, so they can pull out, right? You can pull out. So you can pull out, you can see, these are pull out. These two terms pull out. So I focus on this one, phi, B, phi. But remember, according to what we learned at state transition, this is TF to sigma. Okay, TF to sigma, okay? So then I have pull out TF, okay, pull out TF T0 in here, so I have T0 sigma, B sigma, B sigma, T0 sigma here, transpose. So with this. But remember, according to the definition, phi B, B transpose phi is W. Actually, this is W. It's my definition of W. W times W inverse is I. I times X0 is X0. X0 minus X0 is 0. So this, all the stuff will be 0. So that is sufficiency. So sufficiency is also constructive. So actually you need to find out what is your U to make XTF goes to X0. And necessity is, suppose it's controllable. Suppose this W is not invertible, and then you have XA not 0. So then we can make this one to 0. Okay. Then we can left multiply XA transpose, then still 0 in here. So we end up with this one. By putting XA in here, W definition phi B, B transpose, phi transpose. Then we end up with saying this is a norm definition, okay? And by doing this is XA in here. We are going to see, because this is 0, and we add all the squares together, it should be 0. Then that means this whole thing must be 0. All the positives, all the squares adding together is 0, but everybody is 0, right? Okay, so this guy must be 0. So then otherwise, so this one is a what? Is a compound. So then we just pick up x0 is xa, and we'll be able to start, okay? So in other words, controllability means I can find that there exists U, make this to 0. So that's called necessity, okay? So that xa must be 0. But XA, it cannot be 0, so it's a contradiction. Then, so AB is controllable, then independent role of this one, and all gramian is invertible. So these are all equivalent conditions, okay? And this one is more useful, okay? And it's, again, gramian is an n by n matrix. In other words, invertible means full rank, okay? This is a square matrix and full rank. So, same thing we can get from observability. And observability shows variation of constants. So you have x0, phi, and c, you get a y term. So you derive the output from the output. So you end up with x0 can be uniquely determined if this whole thing has a full rank, linearly independent columns. So then we can, assuming that the two initial conditions are different, then you are going to end up with now space of edge has to be 0. In other words, it's requirement of the range of edges on. So observability is considered as a dual concept of controllability. So that is an advanced topic. So for observability, you only need to focus about A and C. Again, you have a gramian of, so this is actually called gramian. It's phi C transpose C, okay? If this is non-singular, use M and W, be careful, okay? M, here is gramian. So the proof is similar, okay? It's similar. And it's also constructive. So if M is invertible, then x0 inferred by this process is unique. So we multiply phi transpose C transpose both sides. So you end up with this one. This one you do integration, you have M matrix in here times X. So on this side you have phi transpose C transpose Y. So x0 can be obtained from this one and this one. So if this is invertible, then x0 can be uniquely decided. So this is called observable. So that's true. necessarily if it's not invertible, then we get something conflicting. And you come up to this one. Then you end up with this one, okay? So C phi xa is 0. So then that means you cannot observe, okay? So in other words, it's sufficient and necessary for the gramian matrix M is invertible. So this is called observability gramian, okay? Observability gramian. That's a controllability gramian, okay? W, this is an M. So this equivalence then is clear, but this is different to what we learned in LTI system, okay? LTI system. So this is for LTV system, which we live with gramians, okay? Observability gramians. So let me summarize. Today we learned discrete time inhomogeneous system. What do we mean inhomogeneous? Inhomogeneous means I have input U in here, input U. If I don't have this U, then it's called homogeneous, okay? Then we had some basic LTI, linear time invariant characterization of observability and controllability. And so from that, our discussion starting point is regarding the range space and null space using linear algebra concept. And we borrow the concept of gramians. And again, I remind you, M should be no double M, okay? Single M. And we also used the concept of linear independence of vector time function. So next time, we are going to talk about controllability, observability, and of linear time invariant system, okay? LTI system, okay? And please try to read chapter 9 regarding controllability, observability. We have not yet studied anything linked to stability yet. We're going to do that. So we're going to take 5 minutes break, okay?